So we're given the diagram here. I'm going to add a step before find here that's going to be, really without it, we can't solve the problem. And you're going to see a lot more if you continue on to thermo. Is we really need, in this case, an assumption step. So I'm going to assume, for the sake of being able to solve the problem at all, that the two horizontal forces are symmetric about the x-axis. They only tell us their distance apart from each other. They don't actually tell us from the center of the beam their distance. And that does have an impact on the problem. So under the assumption that they are symmetric about x, so they're both going to be 1.5 feet from the center of the beam, is how we're going to do this problem, because we don't really have enough information. And if you look at thermo problems you're going to see next semester, if you're taking thermo, assumptions, you can have 8 assumptions in a problem. Again, these are things that are going to affect your equation writing that might not be given to you. All right, so we have our assumption, we have our given. So what are we asked to find in this problem? Right, so all the support reactions at O. So I'll write that kind of in a vague manner. So all the reactions at point O. So for simplicity, I'm going to represent I'm just going to draw the center line of the beam. So the thickness is going to turn out not to really matter in this problem. All right, so this is the center line of the beam. And I'll keep their coordinate system of x right and y up. All right, so the easy part is just copying down the forces, the external forces that are acting on it. Again, for simplicity, since I'm only drawing the center of the beam here where it matters, this 100 pounds, as long as I put it on that vertical line of action, it doesn't matter if it's acting at the center of the beam externally, if it's acting at the center of the beam or at the top of the beam. So just for simplicity, I'm going to draw at the center of the beam. And same thing for that 200-pound force. Doesn't matter if it's at the bottom of the beam or the center of the beam externally, as long as it's on that vertical line of action. A 120-pound force. Under an assumption of symmetry, I'm going to say that this is 1.5 feet to this point, and it's 1.5 feet from the center to this point. So I have these opposite direction forces. One is 400, one is 360. I can't merely, and this is why the assumption does matter, I can't just combine them and make a couple, which then wouldn't matter where it was placed, because they're opposite directions, but they're not equal. So I can't just take their force times their distance apart. So it will make a difference whether they're symmetric, or the 400 pounds were closer to the axis, or the 360 pounds were closer to the central line. So because they don't tell us, we'll just make the easiest assumption that they're symmetric about the x-axis. But if we made a different assumption, we could turn out with different answers. All right, so those are all the applied forces acting on this. So what else is missing from the free body diagram? Right, so what the wall does, the object of interest, I kind of skipped over that step, but the object of interest I chose is just this beam. I'm not including the wall. So at O, I have to include what the wall does to the beam. So it's a cantilever. You can find it in those 3 sheets of common connections. But again, I wanted to kind of promote thinking about what is restricted from each of the connections, so that if you were to encounter something that was not on one of those sheets, that you know how to think about it. So because it's connected to the wall at O, are we able to move it left or right in the x direction. Right, it's rigidly attached there. We can't pull it out or push it into the wall. Same thing in the y direction. We can't move it in the y direction because it's built in. So it restricts motion in all directions. So at least translation-wise, it's the same thing as a pin. So we can represent in its components the same we would a pin. So we'll have what I'll call OX and OY. So the actual force is at some direction with some magnitude, but as we do in a pin, I'll put it in component form, and then I can see later if I needed to what the magnitude of that force is. All right, so that's the translation. Now in a pin, when something's pinned, it can freely rotate around that pin. But if we look at how it's attached to the wall, can it freely rotate about the x direction because it's built into the wall there? Right, so we can't just rotate it there. It prevents that rotation. So we haven't seen this before in an example, but that means that we're going to have a couple that the wall exerts on the beam. I'm assuming it's positive. Again, I could be wrong, because it could be negative or positive, because whether we want to rotate clockwise or counterclockwise, the wall would stop that. If we had some other type of connection that would restrict rotation around just clockwise or just counterclockwise, then we would know what the direction is, but not the magnitude. So that CO could be positive or negative. OX and OY also can be positive or negative. Right, questions about the free body diagram or the modeling for this one. So if we look at our free body diagram, we have three unknowns, OX, OY, and what I'm calling CO. So our system's in equilibrium. So I erase it for, I'll show in a second here. The equations are true if it's in equilibrium. So for this one, it's going to be pretty straightforward. If we look in the x direction, we have OX plus the 400 minus the 360. So there's only one unknown in equation number one, so we can solve it right away and get that OX is negative 40 pounds. In the y, I assumed OY was up. I have minus 200 plus 120 plus 100. So I can solve equation 2 directly for OY. And OY is going to be negative 20 pounds. Right, so two equations down, two numerical solutions down. So we have the force reactions at O. So now for demonstration purposes, because it comes up as an error many times, we have those two forces. Let's go back. Don't draw it this way, but let's pretend that we modeled this as a pin because we thought, oh, the wall does allow rotation, so it won't have any sort of couple there. So I just have an OX, OY, just like it was a pin. Does that change equation 1 or 2? Right. So in this example, it does not. These are still correct. So we might say, well, there were two unknowns in our picture, which is possible. We wrote two equations, got our two unknowns, and we solved them, so we're done. But what's the possible problem, or what do we need to still check? In general, the moment around any point. Because even if these are correct, and this was the proper way to model it, it still has to be true for it to be in equilibrium, that if we take the moment around any point, it has to be 0. So we still need to check this to make sure that it's true, or that means our assumption of equilibrium was incorrect. So O is our easiest choice here, again, because OX, OY act there. So it's very possible that what we should get, if it's in equilibrium and our modeling is correct, we should get 0 equals 0. So if we look at our right-hand side here, if we start at O, we're going to get negative 200 times 4. We're going to get positive, or plus 120 times 8. We're going to get plus 100 times 11. Minus 400 times 1.5, and minus 360 times 1.5. So if you add up the right-hand side, what do we get for our right-hand side here? Right, so we add up the right-hand side, it's 120, which identically is not 0. So this third equation is not true. 0 is not 120 pound-feet. So this would violate, this not being true violates our assumption of equilibrium, which means that we actually couldn't be, these would not necessarily be true either because we're no longer in equilibrium. So the forces, we might have a net acceleration. This would tell us that we would definitely have a net angular acceleration. So two things are, or a couple of things are possible if this is the case. One, our model is incorrect. The assumption of equilibrium is correct. We just modeled it wrong, which is the example here, or the case here. It could be that even if it's modeled properly, we can't have it, there's no way to put it in equilibrium. It won't be in equilibrium under those conditions. So if this truly were a pin, under these conditions, it would not be in equilibrium because 0 does not equal 0. If we set up the forces differently, it would be possible we would get 0 equals 0 even if this were a pin. Under this, it's not. Or a third possibility is that our math is incorrect and we'd have to rerun that, and if we did, we would get 0 equals 0. In this case, this tells us the first thing we should probably do, since this is a statics course, is reevaluate our model. So this is where we go back. It's possible we missed a normal force from something. In this case, if this was our picture, again, we missed that the wall prevents rotation, so therefore the wall exerts a couple. So in this example, that did not change equation 1 or 2, but it does change equation number 3. The only thing that's different is we should have had plus that CO. Now if we solve equation 3, when it's properly modeled, we get that it can be in equilibrium, or it's in equilibrium when that moment from the wall is negative 120 pound-feet or foot-pounds.